learn how to predict acid-base reactions, learn about organic acids and bases, and Lewis acids and bases. In acid-base reactions, you have two reactants coming together, and the one that's going to act as the acid will have the lower pKa, whereas the one that will act as the base will have a higher pKa. And the equilibrium will favor the side of the weaker acid or conjugate acid. So here we have ethanol and hydronium. So between a pKa of 16 and a pKa of minus 1.7, the hydronium is definitely going to be our acid because that has the lower pKa, which would mean ethanol, this compound, would be our base. Then over here we have the conjugate acid, and this would be the conjugate base. Now if we compare the starting acid to the conjugate acid acid is actually stronger than the starting acid. That means that the equilibrium is going to favor the reactant side because that's the side with the weaker acid. So if you try to do this in the lab, maybe you'll make a very small amount of the products, but mostly you'll have reactants in your flask. So for both of these reactions, predict what the products would be and whether the reaction favors products or reactants, and then use arrows to show how the bonds break and form. So in looking at the reactants here, water is going to be the acid because it has the lower pKa of the two, which would mean this alcohol is going to be the base. So this base, the lone pair, is going to grab an H from the acid. So we'll have grabbed a second H. Now it's going to have a plus formal charge. And then the water will have lost its H, so it forms hydroxide. So this would be the conjugate acid, and this would be the conjugate base. Now the starting acid, water, is much, much weaker than this conjugate acid, which has a pK of around minus 2.4. That means that this reaction will favor the reactants. So that means this reaction doesn't really occur to any appreciable extent. Let's do the bottom reaction. And we use these arrows that go to the right and left to indicate an equilibrium process. So here, our alcohol is going to be the acid because it has the lower pKa, and this is going to be the base. So the base, a lone pair on the base, will grab the proton from the acid, and as a result, we're going to get this conjugate base plus this conjugate acid. So conjugate base, conjugate acid. Now you wouldn't know this off the top of your head, but in a table I'm going to show you in a minute, protonated amines have a pKa of around 9.2. So if we compare the pKa of the starting acid to the pKa of the conjugate acid, we see that the reactants have the weaker acid, so this will also favor reactants. With organic acids, they are characterized by the presence of a positively polarized hydrogen atom. So notice that here the hydrogen is attached to an oxygen atom, in that the oxygen is really pulling electron density away from the hydrogen, which is also shown by these electrostatic maps where the blue indicates a partial positive and a red indicates a partial negative. So this H is electron deficient and it is acidic. And the same is true with acetic acid, which is a carboxylic acid. So this H is also acidic. In fact, it's a lot more acidic than the H in methanol. Notice the difference in pKa values. It's almost, it's more than 10 pKa units smaller. And remember, this is a logarithmic scale, so if acetic acid is 10 pKa units smaller, that means it's 10 to the 10 times more acidic. And then acetone is the next compound. So these hydrogens are all electron deficient and can be removed by a base. And the pKa here is 19.3. So this is a much weaker acid than acetic acid, and it's a weaker acid than methanol. Organic bases have an atom with a lone pair of electrons that can bond to hydrogen. So interestingly, sometimes we will see that the same molecule could have acidic hydrogens, but could also act as a base. So acetone, which we saw in the other example, these hydrogens we said were acidic, but this oxygen could act as a base. The same thing with methanol. This oxygen can act as a base, and with amines, the nitrogen, which has a lone pair, can act as a base. So notice the sites that can act as bases all have lone pairs. So if a compound could act as an acid or a base, the function that it will take depends on what it's reacted with. So oxygen-containing compounds can react as bases if they're paired with a strong acid, but they could also act as acids if they're paired with strong bases. Stronger acids tend to be weaker bases, whereas weaker acids tend to be stronger bases. So carboxylic acids, shown here, tend to be fairly strong organic bases. I mean, they're not as strong as HCl, but as far as organic bases go, they're fairly strong. And then amines would be fairly weak acids. But in contrast, amines are fairly strong bases. When an acid is protonated, the resulting conjugate acid is even stronger. So the conjugate acid of ethanol, look how much stronger of an acid it is. Its pKa is minus 2.4. When you get the conjugate acid of an amine, its pKa is much smaller than the starting pKa. Here is a handy-dandy chart that shows the pKa's of a variety of organic and inorganic compounds. Something to notice here is that we have strong acids here at the top, and the increasing acid strength correlates with a weaker conjugate base. So the stronger the acid, the weaker the conjugate base. We've been working in the realm of the Bronsted-Lowry acid and base definition, where we were only concerned about the movement of a proton of an H+, but there's a second type of definition we can use to describe acids and bases, which is the Lewis definition. And the Lewis definition focuses on electrons. A Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. Now, sometimes something could be both a Lewis base and a Bronsted-Lowry base. However, a Lewis acid and a Bronsted-Lowry acid are not going to be the same thing. So the key characteristic of a Lewis base is that it has a lone pair, and the key characteristic of a Lewis acid is that it has a vacant orbital. And the most common type of Lewis acid that we'll see is any type of boron-containing molecule. And here would be an example of boron trifluoride. So boron has an incomplete octet. It's actually sp2 hybridized, and it has an empty p orbital that can accept electrons from a Lewis base, and that's what's happening in this reaction.